Today we will start our second lecture of artificial intelligence. In the first lecture, we introduced certain things, namely what artificial intelligence is all about, the definition of intelligence, and we looked at several example AI systems, and we also traced the history of AI. Today, we will go to the second part of this introduction, where we will talk about intelligent agents. Since in a major part of this course, we will talk about the various aspects of an intelligent agent. Today, we will introduce what an intelligent agent is and how we look at intelligent agents. So, now to describe the instructional objectives of today's lecture, we like to define an agent, define an intelligent agent, what we mean by intelligence as an agent, define a rational agent. In the last class, we talked about rationality. We will talk about what we mean by a rational agent. Then we will explain the concept of rationality as we see, or the concept of bounded rationality, which we will deal with. We will discuss the different characteristics of the environment in which the agent operates, and we will explain different agent architectures. On completing this lesson, you will be able to understand what an agent is and how an agent interacts with the environment. As we will see in the course of this lecture, the environment is an important component of the agent design, and the agent should be designed so that it can work properly in its environment. After you have taken today's lecture, you should be able to do the following. When you are given a problem situation, you should be able to identify which are the percepts available to the agent, or what the agent can sense, and how the agent should act so that to optimize its performance. We should also look at what are the performance measures by which we should evaluate an agent to try to see if the agent design has been successful. And we will we hope to understand what we mean by the definition of a rational agent, what a rational agent is. We will also look at the concept of bounded rationality, which is the rationality that we will deal with. So, in summary, we will be familiar with the different agent architectures, including stimulus response agents, state-based agents, deliberative or goal-directed agents, utility-based agents, as well as learning agents. And you should also be able to identify, given a problem situation, the characteristics of the environment and recommend what the architecture of the desired agent should be in this environment. So, this is our agent. The agent operates in an environment. The agent operates in an environment. The agent receives percepts from the environment, and the agent acts, and its actions can change the environment. The agent uses its various sensory organs. So, depending on the sensors that the agent has, for example, the agent may be able to see if the agent has a camera, agent may be able to hear if it has a sonar sensor, and so agent can see or hear or accept different inputs from the environment. Inside the agent, there is an agent program which decides on the basis of the current percept or the percept sequence that it has received till date to decide what should be the good action to take in the current situation. So, the agent has actuators or effectors to take actions. So, these actions can potentially change the environment. These actions can change the environment, and the agent can use its sensors to sense the changed environment. So, we see that the agent does the following things. The agent operates in an environment. The agent perceives its environment through its sensors. The agent acts upon the environment through actuators or effectors, and also the agent has goals. Goals are the objectives which the agent has to satisfy, and the actions that the agent will take will depend upon the goal that it wants to achieve. So, what is a percept? The complete set of input at a given time that agent gets is called its percept. The input can be from the keyboard or through its various sensors. The sequence of percepts, maybe the current percept or maybe all the percepts that the agent has perceived so far, they can influence the actions of an agent. The agent can change the environment through effectors or actuators. An operation which involves an actuator is called an action. So, agent can take action in an environment through the output device or through the different actuators that it might be having. These actions can be grouped into action sequences. So, we have already seen the agent has sensors and actuators and has goals, and the agent program implements a mapping from percept sequences to actions. So, the agent program implements a mapping from percept sequences to actions. We also have to talk about a performance measure by which we will evaluate an agent, evaluate how successful the agent design has been. And finally, we will like to talk about autonomous agents. In artificial intelligent agents, autonomy is extremely important. The agent should be able to decide autonomously which action it should take in the current situation. So, an autonomous agent decides autonomously what action to take in its current situation in order to maximize its progress towards its goals. So, if the agent has a goal, the agent should try to maximize its goal so that its performance is maximum. So, the behavior and performance of intelligent agents we will look at in terms of the agent function. An agent function is, as we have already talked about, is a mapping from perception history to action. Now, what is the mapping that the agent should implement? In order to, so the obviously the mapping that the agent should implement is the one which maximizes its performance measure. The ideal mapping of an agent specifies which action an agent should take at any point of time. We will talk presently about how the agent should achieve this maximization. The performance measure is in fact a subjective measure which characterizes how successful an agent is, and how the performance measure is characterized can vary. The performance measure could be the amount of how rich the agent will become if the agent behaves in a particular way, or how quickly the problem can be solved, or how precise or how good the solution is, what is the quality of the solution that the agent has been able to achieve, the amount of power. The agent's objective may be to minimize the amount of power consumed, or the performance measure could be a combination of several of these factors. Now, let us look at, you see, actually an agent could be anything. We can look upon a human being as an agent, we can look upon a calculator as an agent. So, in order to characterize something as an agent, we have to look at the different characteristics in terms of the different the mappings the agent performs, its percepts, its actions, the environment it operates on, the characteristics of the environment, and certain other things. So, let us look at some common things that we are familiar with and look at what are the characteristics associated with such agents. We are all familiar with human agents. So, what are our sensory organs? We can see with our eyes, we can hear with our ears, we can smell, we can touch, we can taste. These are the 5 primary input mechanisms that we possess. What are the actuators that we possess? We have our hands with which we can take some action, we have our fingers, we have our legs, and several other things, our mouths, with which we can take our actions. Now, if we design a robot, what are the percepts, what are the different sensory organs that we can give to the robot, that we can build into a robot? We can have a camera with a robot, a camera with which it can take pictures of what is it in front of the robot, and the robot function or the robot program can analyze that image and find out salient characteristics of the environment, which will decide the way it should act. Then the robot can use other types of sensors like sonar sensors, infrared sensors, etc. And the type of actuators that we can build into a robot are wheels, speakers, lights, grippers, any other output device that we may want to. And then we can look at a software agent. The software agent is becoming increasingly common nowadays. So many people call them soft bots. These soft bots have some functions as sensors. They compute a function of the input. So they have some functions as sensors and functions as actuators. We will later look at some specific software agents to look at the sort of function which they take as their input and the sort of function they compute to give their output. So this is an example, this is a picture of our robot. This is the Xavier robot developed at CMU. It's one of the earlier robots which were developed at CMU. Then this is a robot called the COG robot, which was developed by Rodney Brooks' group at MIT. So let's go to the home page of this robot. So we will have occasion to talk more about Rodney Brooks' activities in the course of today's lecture. So the basic motivation behind creating COG is the hypothesis that they wanted to build a humanoid robot, a robot having intelligence like a human being. So, this picture may be too small for you to see, but this shows Rodney Brooks. Professor Rodney Brooks is with the robot COG. So, you may like to visit the site and get more information about the COG robot. And thirdly, we have this entertainment robot. This Aibo robot is sold by Sony. So, this robot is they claim that it is autonomous, it is sensitive to its environment, it can learn, it has different stages of its life, and it can be personalized according to the environment in which it grows up in. And then there are other types of agents like soft bots or software agents. For example, there are sites like askjeeves.com, which is an example which you can consider as an example of a software agent. Then there are various expert systems, including medical expert systems, for example, the cardiologist, which are also software agents. Other than software agents, we have other types of robots, for example, the autonomous spacecrafts like the Mars rover that we talked about in the last class. And then there are other types of robots like intelligent buildings, which have intelligence built into them to decide the lighting condition, air conditioning, etc. So, an intelligent agent must have certain fundamental faculties. It should be able to act. An intelligent agent must act. The intelligent agent must sense its environment, and so an agent must sense its environment. If the agent acts without sensing, that is blind action, and blind action cannot be intelligent. So, there are certain types of architectures where the agents can sense and act, and the agents don't perform any deeper deliberative action. In fact, robotics is about sensing and acting only. At the outside, we only require the agent to act appropriately. Understanding is not necessary. Understanding may be important for choosing proper actions, but understanding by itself may not be necessary. However, we must realize that sensing really needs understanding to be useful. So, an intelligent agent which possesses complete intelligence must be able to do the following. It must be able to understand or interpret what it senses. It should be able to reason. And finally, the agent should also be able to learn so that the agent can operate in an unknown environment. In fact, learning is a prerequisite for an agent to be autonomous. An autonomous agent which can adjust to a changing environment must have some learning component. And also, intelligent agents must be rational. In artificial intelligence, in this course, we will talk about building rational agents, and we will talk about different aspects that rational agent has and look at these subfields. Now, what is a rational agent? A rational agent is an agent which always does the right thing. Now, what is the right thing? So, in order to understand that, we must understand what are the functionalities or the goals of the agent. What are the components of the agent, and we must look at how we should build these agents. Perfect rationality assumes that the rational agent knows everything and will take that action which maximizes her utility. So, perfect rationality is equivalent to demanding that the agent is omniscient or all-knowing. If the agent knows everything and the agent can reason extremely fast and everything is, then the agent is a perfect rational agent. However, a perfect rationality is something which is not within our scope of, not even within the scope of human beings. We do not satisfy the definition of perfect rationality. We are not omniscient. There are many things which we do not know. There are many things which we cannot reason in a reasonable time frame given what we know. The concept of bounded rationality was introduced by Herbert Simon of CMU in 1972 in his theory of economics. So, bounded rationality says that because of the limitations of the human mind, humans must use approximate methods to handle many tasks. So, bounded rationality does not aim at maximizing the absolute utility of the agent, because that is something which may not be achievable given a realistic agent, given realistic resource bounds. So, instead, rationality, as we will look at, will concentrate on using approximate methods where appropriate, so that the agent can take the best action given its resource limitations and given what it already knows. Rational action is the action that maximizes the expected value of the performance measure given the percept sequence to date. Now, when an agent takes an action, the action may not always have the same outcome. Sometimes the outcome of the action may be good, sometimes it may be bad. So, when we talk about rationality, we must look at the expected value of the performance measure, not always the absolute value of the performance measure. Also, we must evaluate an agent not on the basis of how it should behave in a perfect case, but how it can behave based on what it can sense. So, something that the agent cannot sense or foresee, we cannot hold the agent responsible for those things. Therefore, rational action in the light of bounded rationality talks about maximizing the expected value of the performance measure given the percept sequence which is available to the agent. So, does rational action means the best action? Well, the answer is yes, but to the best of the agent's knowledge, based on what percepts the agent already has access to. Does rational mean optimal? Yes, to the best of the abilities of the agent and subject to the resource constraints. The agent may have limitations in the way it can act. The agent may have limitations in terms of the resources that it has access to. There could be time limitations, there could be space limitations. So, given these constraints, given its abilities, the agent should take the best action that is expected to maximize its utility. That is the rationality that we will talk about. We must understand that a rational agent need not be omniscient, because it does not know the actual outcome of its actions, and certain aspects of the environment may be unknown to the agent. So, rationality takes into account the limitations of the agent, the percept sequence it has access to, the background knowledge the agent has, and the actions that the agent can take, and we only deal with the expected outcome of actions. So, as we have already talked about, in 1957 Herbert Simon proposed this notion of bounded rationality. Formally, if we define bounded rationality, it is that property of an agent that behaves in a manner that is nearly optimal with respect to its goal as its resources will allow, as nearly optimal as its resources will allow. Now, we come to another very important component of an agent. The agent, actually the design of the agent depends a lot on the environment in which the agent operates. And the environment, the task environment of the agent can be defined in many different ways. So, we will look at several ways of characterizing the environment, and there are two ways of characterizing the environment, one in the absolute sense, the other from the point of view of the agent. For example, when we want to talk about whether an environment is deterministic or stochastic, we must not look at whether the environment is deterministic from an absolute point of view, but rather whether the agent appears, whether the environment appears deterministic to the agent based on what it can perceive. Now, environments can be divided into two types based on the observability of the environment. An environment may be fully observable or it may be partially observable. If the environment is fully observable, all of the environment which is relevant to the action being considered is observable. All the relevant portions of the environment are observable. On the other hand, in the case of partially observable environments, not all the relevant portions of the environment may be observable. The relevant features of the environment are only partially observable. For example, consider an agent playing chess, like the Deep Blue chess playing program. The agent has complete knowledge of the board. So, everything about the environment is accessible to the agent. So, the chess environment is a fully observable environment. Consider again the environment where the agent is playing pokers. So, the agent cannot see the hand of the opponent. So, the environment in this case is only partially observable to the agent. So, if the environment is fully observable, the agent need not keep track of how the environment is changing and deliberating about the environment. So, if the environment is partially observable, the agent, in order to behave successfully in such an environment, has an added task of keeping track of the environment and reasoning about the properties of the environment. Then, if you look at the aspect of determinism, again environments can be divided into two or three types. Deterministic environments, in deterministic environments, the next state of the environment is completely described by the current state and the agent's action. So, when an agent, we have already seen when we looked at the diagram of the agent environment, that the agent's action changes the environment. Now, in a deterministic environment, given the agent's action, how the environment changes is deterministic. There is no other unknown thing which comes into the picture to decide how the environment changes. In stochastic environments, on the other hand, there is some element of uncertainty. Therefore, how the environment changes depends not just on the action that the agent takes. Now, as I was saying just now, whether an environment is deterministic or stochastic depends on how you look at the environment. If you cannot observe the environment fully, the environment may appear stochastic to you, whereas it is actually deterministic if you have access to the entire environment. For example, take the example of pokers again. If the agent did have access to both the player's hands and all the cards which are there, then the environment actually behaves in a deterministic way. However, when it is partially observable, it appears to be a stochastic environment. So, this is an environment which appears to be stochastic because of partial observability. If you look at the game of Ludo, it is a stochastic environment because the environment, how it evolves, depends on the value which the die has rolled. So, whether the die has rolled 1 or 2 or 6, depending on that, the agent can decide its action. So, this is a truly stochastic environment. A strategic environment is an environment state which is wholly determined by the preceding state and the actions of multiple agents. So, a strategic environment, in a strategic environment, apart from the current agent, the agent itself, there are other agents around, and the actions of all these agents influence the environment. A strategic environment is one where the environment is only changed by the actions of the agent itself and other agents. For example, chess. A chess playing agent operates in a strategic environment. Then, if we look at the episodicity of an environment may be episodic or sequential. An episodic environment is one where subsequent episodes do not depend on what actions occurred in previous episode. First of all, sometimes certain tasks can be divided into different phases or different episodes. In such episodic environments, the one episode may or may not influence the subsequent episode. So, if one episode does not influence the subsequent episode, such an environment is called an episodic environment. So, in such an environment, an agent did not plan beyond episodes. In a sequential environment, on the other hand, the agent engages in a series of connected episodes. So, subsequent episodes are dependent on what happened in the previous episodes. So, the agent, in this case, the agent may need to plan ahead or base its action upon what happened in the previous episodes. Then, if we look at another characteristics of the environment based on its dynamism, environments may be static or dynamic. A static environment does not change by itself. So, an advantage is that a static environment does not change when the agent is deliberating. So, the agent does not need to observe the world during its thinking process. A dynamic environment changes by itself, that is, apart from the action that the agent takes. Also, another dimension by which we can characterize environments is by its continuity. An environment is discrete or continuous. An environment is discrete if the number of distinct percepts and actions are limited, and the number of states are limited. If the number of states are discrete, then the environment is a discrete environment. An environment is a continuous environment if the range of percepts is continuous, or range of actions that it can take is many, or the number of states is either continuous or too many, so that we treat them as continuous. And finally, we can also characterize by the environment according to whether there is one agent which we are talking about in the environment, or whether there are other multiple agents in the environment. So, that is, if the environment contains other agents, then it is a multi-agent environment. In game, when we look at two-person games, we usually talk about one opponent agent. There are environments where there is a single agent, but so for many tasks that the agent does, usually we talk about a single agent environment. But there are many situations which require distributed agents, or in social and economic systems we deal with multiple agent systems. So, the complexity of the environment includes knowledge-rich environments and input-rich environments. In knowledge-rich environments, there is enormous amount of information that the environment contains. Knowledge-rich environments contain lots of information. An input-rich environment is one where there is an enormous amount of input, enormous amount of percept that the agent can get. And in such environments which are complex, which are either knowledge rich or which are percept rich, the agent must have a way of managing this complexity. So, such considerations, when the environment is complex, the agent must develop its strategies for sensing or its strategies of attentional mechanisms. The agent must decide selectively what to sense, what is more relevant, and what it should give its attention to, rather than deal with the entire complexity of the full environment. So, an agent needs to focus its effort in such rich environments. Now, we will look at the different types of agent architectures. Table-based agents, stimulus-response agents, goal-based agents, utility-based agents, and learning agents. We will briefly talk about these agent architectures. A table-based agent is a very simple agent, where you see we have said that an agent has to take actions given its sense, given what it senses, given its percepts. Now, in a table-based agent, the mapping from percepts to actions is stored in the form of a table. So, on the left side we have the percepts, and on the right side we have actions. So, and the behavior, the agent program is extremely simple. So, given the percept, the agent looks it up in the table and decides what action to take. So, based on this mechanism, we can develop what we call reactive agents, which can take the action depending on the percept. Unfortunately, the best action for the agent depends not only on the current percept, but on the percept sequence. Now, the number of possible percept sequence can be very large. In fact, it can be infinite if the agent acts over many time steps, many unbounded time steps, then it can become infinite. So, this table can become very large if you have a mapping from percept sequence to action. In case of simple tasks where the action only depends on the current percept, it may be easy to develop a table-based agent, but it is infeasible when the action, correct action or the best action depends on the past and not only what the agent sees or perceives at the current time step. So, as I have already said, a table is a very simple way to specify a mapping from percepts to actions, but tables may become very large. And in a table-based agent, there is no intelligence in the agent himself. All the work is done by the designer in designing the table. So, designer makes the table, the agent just looks it up to decide how to act. So, such agents have no autonomy. All actions, all behaviors are predetermined, and there is really no concept of learning. Now, the mapping from percept to action may be done in different ways. It may be in terms of an actual table, it may be in terms of a production system or rules. This mapping can also be implemented by neural networks, or one can implement the mapping by an algorithm. So, this mapping can be implemented in a rule-based manner using a neural network or using some algorithm. So, such agents where the action depends only on the percepts and there is no deliberation involved, they are called reactive agents. So, this term reactive agents means those agents whose information come from sensors and they can take actions through their actuators or effectors. And we can additionally assume that the actions changes the current state of the world, and the agent can only take some action without any deliberation. Such agents are also called stimulus response agents. They have no notion of history. All their history is encoded in the current state as the sensors see it right now. Now, at this point, we will talk about Professor Rodney Brooks of MIT and the subsumption architecture that he has proposed, which is based on stimulus response agents. In 1986, Professor Rodney Brooks gave this notion of the subsumption architecture. His argument was that lower animals behave in a largely reactive manner. They have very little sense of deliberation. So, they have most of their actions are reactive actions. And his argument was that in the time scale of evolution, reactive behavior came much earlier than deliberative behavior, and he has been able to show that simple reactive behavior, a number of such components having simple reactive behavior, can achieve a surprising degree of intelligence. So, Brooks' idea has been to follow the evolutionary path, how life has evolved, and build simple agents for complex worlds, a combination of simple agents which can work well in the complex world. The features of his subsumption architecture are that there is no explicit knowledge representation. behavior is not centrally controlled, but behavior is distributed among different components. The response to stimulus is reflexive, and importantly, the design is bottom up. The complex behaviors are fashioned from combinations of simple behaviors. Simple behaviors are put together to achieve complex behaviors, and each individual agent is simple and inexpensive. So, in the subsumption architecture is basically a layered architecture. So, as I mentioned, according to Professor Brooks, the time scale for evolution has been 5 billion years. It has taken 5 billion years to evolve from single cells, since cells evolved to the present day. The first humans appeared 2.5 million years ago only, whereas the first cells appeared 5 billion years ago, and symbols did not appear until only 5,000 years ago. And therefore, his proposition is that we should look at simpler behavior as the first step towards building intelligent agents. So, in subsumption architecture, there are different layers of behavior, and higher layers override lower layers, and each activity in each layer consists of a simple finite state machine. Now, this is an example of a simple architecture proposed by Rodney Brooks. In this system, there are several layers. This is a very simple robot. In the layer 0, there is the avoid obstacles layer. Layer 0 is the avoid obstacles layer. In this layer, there are several sensory organs. The sonar component generates sonar scan. The collide component sends halt message to forward, and the field force component is the signal sent to run away or turn around. So, layer 0 of the agent is to avoid obstacles. This is the first layer of the agent, which enables the agent to navigate in an environment without colliding with other agents. So, very simple behavior of a navigating robot without using a lot of deliberation. In the second layer, or the layer 1, there is the wonder behavior. This wonder behavior generates a random heading. It allows the robot to occasionally wander. So, in the wonder layer, there are two components. One generates a random heading, and secondly, the avoid component reads repulsive force and generates new heading and feeds that to turn and to forward. Layer 2, that is the third layer, has the exploration behavior. So, this has several components. The when look component notices whenever there is idle time, it looks for an interesting place. The path plan component sends new direction to avoid. The integrate component monitors path and sends them to the path plan. So, as we have seen, these percept based agents are efficient because they do not require internal representation for reasoning or inference. However, there is no strategic planning or learning, and they are not good for multiple opposing codes. In the second type of agent, the more knowledge rich agents, we come to state based agent. In state based agents, information comes from sensors, and it changes internally the agent's current view of the world based on the state of the world and the knowledge the agent has, it triggers action through the effectors. And in order to do this, the agent does some deliberation. So, based on the state of the world and knowledge, the agent chooses the actions and carries out the action through the effectors. Now, in goal-based agent, the agent's action depends upon its goals, and goal formulation is based on the current situation. So, based on the goal that the agent has to achieve and the current state of the agent as it perceives, the agent goes through some deliberations to decide what should the next action be. We will look at search and planning. These are the two fields of AI in which we will look at different ways of deciding what action to take in order to achieve the agent's goals. So, in goal-based agents, the sequence of steps required to solve a problem is not known a priori. They are not available in a table, and they must be determined by a systematic exploration of the alternative actions by deliberations. Then thirdly, we have utility-based agents. Utility-based agents are akin to goal-based agent, but they are a more general framework. If an agent has several goals and it can achieve only some of them, these goals may have preference associated with them. Which goals are more preferable? So, in this case, we can talk about utility-based agents, where we have different preferences for different goals. A utility function is a very general function that maps a state or a sequence of states to a real valued utility. So, a state is mapped to a utility value, and we can say that the goal of the agent is to maximize its utility, or the goal of the agent is to maximize its expected utility. When we look at decision theory, we can consider agents which are based on utility. And finally, and very importantly, we have learning agents. We have said that learning is an extremely important component of autonomy. An autonomous agent should have some learning built into it. Learning allows an agent to operate in unknown environment, and the learning element modifies the performance element, and learning is required for true autonomy. We will take up learning later in this course when we will look at several types of learning that are can be carried on by agents. So, in summary of today's lecture, an agent perceives and acts in an environment. It has an architecture, and an agent is implemented by an agent program. An ideal agent chooses the action which maximizes its expected performance. An autonomous agent uses its own experience rather than built-in knowledge of the environment by the designer. An agent program maps from percept to action and updates its internal state. Reflex agents respond immediately to percepts. Goal-based agents act in order to achieve their goals. Utility-based agents maximize their own utility function. And then, in order to have goal-based agent, the agent must represent its knowledge, must represent its history, must have some background knowledge. This we will study when we look at state-space search. So, representing knowledge is important for successful agent design. So, we will come to now to a set of questions based on today's lecture. Question 1, define an agent. Question 2, what is a rational agent? Question 3, what is bounded rationality? Question 4, what is an autonomous agent? Question 5, describe the salient features of an agent. Question 6, find out about the Mars rover. What are the percepts for this agent? Characterize the operating environment for this agent. What are the actions that this agent can take? How can one evaluate the performance of this agent? What sort of agent architecture do you think is most suitable for this agent? Question 7. Answer the same questions above for an internet shopping agent. With this, we complete today's lecture. Thank you.